Hello, in this video we are continuing our discussion of section 7.1 on areas between curves. In this example we have been asked to find the area of the region that's enclosed by the curves x equals y squared and x equals y plus 2. Now we're going to do this by first sketching the enclosed region. We're going to label all of the necessary, all of the helpful pieces. And then in part B, we're going to set up and evaluate the integral that gives the area of the region with respect to y. Part C, we're going to do the same thing, find the area of the region, but now we're going to integrate with respect to x. This is one of those cases when it is actually possible to rearrange both functions and find the area with respect to either one of the variables, but you will notice as we work through the solution that one of the options is significantly easier than the other, which is the case the vast majority of the time. And sometimes you will have functions that cannot be rearranged. So then you will have to set up your area in terms of whichever function or whichever variable you have your functions written in terms of. So you need to be able to find area with respect to either y or x. So we are going to practice both in this example. So first off, for part A, we are going to draw a sketch of the region. Now, first off, let's graph x equals y squared. Well, that's a parabola. Since it's x equals y squared, it means that we are going to open right or left because of the fact that y is being squared. And then the positive value in front of the y squared means we're going to open to the right. The vertex is 0, 0. We don't necessarily need more detail than that as of right now. Let me move this up a bit. So we're going to have something like this. Okay, you could find some different values here if you'd like to, but we're not going to need them quite yet. So now let's deal with our other equation, x equaling y plus 2. Well, notice this is really easy to rearrange. If we do, we get y is equal to x minus 2, which is a line. The slope is 1. The intercept is -2. So this means that we are going to cross the y-axis at -2. We're going to have a slope of 1 up from there. So we're going to go through the point 1, 1, which conveniently enough is also a point on the parabola. So we should have something like this. Y equals x minus 2. Problem does ask us to label everything, so let's go ahead and label the x equals y squared. So we have, we're asked to find the area of the region that's enclosed. So that means that we need to find the area of this region here. Okay, so for our bounds of integration then, they're going to depend on these two intersection points. Well, we already found one of the intersection points. It just sort of fell out from when we were graphing. The other intersection point you could figure out by, sort of guess and check. It wouldn't be that hard to figure out. Or you could find your intersection points by setting the two equations equal to each other. So that would be y squared is equal to y plus 2. So this is a quadratic equation. We can factor this and solve. Y minus 2, y plus 1. So we end up getting y is equal to 2 and y is equal to -1. And I am sorry, I definitely labeled that incorrectly earlier. This should be the point 1, -1. Sorry about that. So that comes from here. You could also take this and substitute it into either one of your equations. X would be equal to -1 squared, so that's 1. For the other intersection point, you're going to take y equals 2, so x is going to be 2 squared, which would be equal to 4. So that means that our other intersection point is the point 4, 2. Okay, so we have our two intersection points. We have our two curves, and we have the region that we are finding the area of. So according to the description for part A, you would not need to necessarily shade in the area, but you would need to have both of your curves labeled, so x equals y squared, y equals x minus 2, or you could label it as x equals y plus 2, that's fine. And you would need both of these intersection points to be labeled. You wouldn't necessarily need to show this work, but you can if you would like to, or if it's helpful to working out the problem. So this is part A. Part B asks us to set up and evaluate the integral that gives the area of the region with respect to y. So if we are finding area with respect to y, it is helpful to remember right minus left. Now in this case, for this region, the function that's given by the line, so that's x equaling y plus 2. Let me write it down here so we can see. For the shaded region, x equaling y plus 2 is to the right for that whole region. So the right function is going to be x equaling y plus 2. The left function then is going to be y squared. We are integrating over y values. So from y equals something to y equals something else. These come from our intersection points. The lower value for y is -1, the larger value is 2. So we're going to integrate from y equaling -1 to y equaling 2. So this means that our area is going to be the integral from -1 to 2 of y squared minus the whole function. Oops, sorry, I definitely switched that. Y plus 2 minus y squared, that's better, and then dy. So just a couple of simple antiderivatives here. 1/2 y squared plus 2y minus 1/3 y cubed. This gets evaluated from -1 to 2. And we can plug in our bounds there with some arithmetic. 1/2 2 squared plus 2 times 2 minus 1/3 2 cubed minus 1/2 -1 squared plus 2 times -1 minus 1/3. Let me squeeze this in here. -1 cubed. A little bit of arithmetic. This should give us 9/2. Now this is an application problem, but we don't have specific units. But it's still good to remember to write units. If you were given units in the problem, you would need to include them at the end. So you might as well just go ahead and write a general squared units here. So the area is equal to 9/2 square units. This is what we've gotten for part B. Part C tells us to find the area of the same region with respect to x. But the one thing I want to notice is that this is the same region as in part B. Which means that we should get that our area is equal to 9/2. So that gives us something to check our final answer. So, to find the area with respect to x, we first off need to remember that for integrating with respect to x, we need to have a top and a bottom function. Well, that wasn't helpful. So the area is going to be the integral from a to b of top minus bottom. But we need to identify what our top function and our bottom function is. So going back to our sketch up here, we have two intersection points, 1, -1, and 4, 2. That's what we got by setting our functions equal to each other. But these functions were written in terms of y. So the first thing we should do is figure out what our functions are in terms of x. Well, one of them we've already found, y equals x minus 2. But the parabola, if we were to solve for y, we would need to take the square root of both sides. And whenever you take the square root of both sides, you have to remember plus or minus. So this means that we actually have two functions here. If we were to label this on our graph, the bottom half of our parabola would be given by the negative square root. So this is y equaling negative square root of x. Whereas the top half of the parabola is the positive square root. So now we have another intersection point that we have to consider, and that is right here, where the positive square root and the negative square root intersect. That is the intersection point 0, 0. Now, since we have three functions, this is a pretty good indication that finding the area of this region in terms of x is going to be a little bit more complicated. Because if we think about splitting our region here, because we have this intersection point at 1, -1, notice that to the left of x equaling 1, our top function is the square root of x, and our bottom function is the negative square root of x. Whereas to the right of x equaling 1, the top function is still the same, but the bottom function is our line x minus 2. So what this means for the area is we're going to have two regions. The first region is for x values between 0 and 1. And for this region, our top function is the square root of x, and our bottom function is the negative square root of x. So then our first area will be the integral from 0 to 1 of the square root of x minus negative square root of x, and all of that dx. Our second region, A2, this is for x values between 1 and 4, where 4 comes from our other intersection point. Now the top function is still the square root of x, but the bottom function is our line written in terms of x, so that's x minus 2. So then our second area is going to be the integral from 1 to 4 of the square root of x, square root of x minus the function x minus 2. We are subtracting that whole thing, and then dx. So our total area, which is really what we want in this case, is going to be the integral from 0 to 1 of the square root of x minus negative square root of x dx plus the integral from 1 to 4 of the square root of x minus 2 dx. So then, simplifying this before we integrate, because it'll be a little bit less work that way, if we have minus and negative square root of x, it's going to be the same thing as plus the square root of x. Sorry, I don't know where the 2 comes from. So then we're going to have the square root of x plus the square root of x, which gives us 2 square root of x dx. Then we'll have plus the integral from 1 to 4 of the square root of x minus x plus 2 dx. Remember, when you're integrating the square root function, it's helpful to write it as x to the 1/2. So we end up with x to the 3/2, we'll have 4/3. That gets evaluated from 0 to 1. Then we're going to have x 2/3, x to the 3/2 minus 1/2 x squared plus 2x. All of this gets evaluated at 1 and 4. You can plug in your bounds. You should get 4/3 minus 0 for the first one, plus 2/3, 4 to the 3/2 minus 1/2, 4 squared, plus 2 times 4, and then minus 2/3 minus 1/2 plus 2. All of this worked out together. Remember, if you want to work this out without a calculator, you can write this as 4 to the 1/2 cubed. 4 to the 1/2 is the square root of 4, so that's 2 cubed, so that's going to be 8. Okay, but all of the arithmetic here, we know our final answer should be 9/2. And again, we're going to have square units. So our area here is 9/2 square units. And I don't care how you write out square units, whether it's all in words or units squared like that, either one is fine.